difference with spot. So, particle. That is the answer question.
Ah,
Okay.
okay. I hope like everyone in Zoom can hear me. Uh, yeah. So this presentation is like an updated version of like one of my previous presentations. Like so, so in this project, like we are like working on like fabricating diffractive deep neural networks, working in the visible wavelength. And for that, we are doing like quantization aware training of D2NNs for that purpose. And so I'll start with like a brief introduction to diffractive deep neural network for anyone like who's not familiar with them. So these networks have like a set of diffractive optical layers, and they're so we can like use them to like physically realize a neural network. And they work on like optical optics, and they use this other harness the power of optics like to do inference as almost as fast as the light of speed. And also these networks like operate with passive elements, so we do not require to give like additional energy to do the computations. Yeah. And so there are like many applications in this D2NN. So recently they've been used like for image classification, 3D object detection, salience segmentation, and also all optical phase image. Ah, yeah. Ah, yeah, sure. Yeah, yeah, sure. Yeah. Uh, okay. So like when we are like, so I go into like the process of training D2N, like physically realizable D2N. So we can like identify three main steps in this. Like the first one is like we need to differentiably model the optics in the D2N so that we can train this like using like a gradient based method. And then after the modeling, we can train the parameters of the D2NN, these optical parameters to perform like a given task. And finally, we can do the fabrication after, after training these parameters. And so going from the simulation, that is going from this trained network to the physical realization. So we consider D2N, especially the ones operating in visible wavelength, they have like really small features. So for an example, if we consider a D2N working in operating in the wavelength of like 632 nanometers, the neuron size, like the small features in this network, about half that size, that is like 316 nanometers. And the entire D2N is like in the micrometer scale. And these smaller features actually cause like challenges in physically realizing these networks. So mainly like there are like limitations in the fabrication process that we have to use like in this sort of situation. Like there can be limitations in the like the precision of the weights that we can fabricate. And also there can be limitations to the range, like the maximum value that we can like fabricate like for weights. And also there can be issues with structural rigidity of this fabricated network. And also there can be limitations on the smallest feature size that we can fabricate. And also there can be like other noise and artifacts that come into play like when we are going to like physical realization. So to address these challenges, like we have to add like couple of more steps into our like pipeline that I discussed earlier. So we can differentiably model the D2N. Then we can train the full precision model as I explained earlier. And after that, to account for the lack of precision, we have to do like a quantization aware training of this of the parameters. And then also we have to improve the robustness to noise and other artifacts. And finally, we can do the fabrication. So I'll be mostly talking about this quantization aware training, so that which is the main focus in this project. So I'll be from this point onwards, I'll be mostly talking about that. So first of all, I'll just give an idea about how to like differentially model a D2NN. So if we consider a D2NN like this, so which has M layers like this, and we have like an incoming field, and there's a detector to capture the output. And so if we consider like a neuron in one of these layers, so each of these neurons has like a complex transmission coefficient. So with an amplitude and a phase coefficient. So these are the parameters that we are optimizing in a D2NN to do a given task. And so the way like the income field to each of these neuron depends on all the as a summation of all the layers coming from the previous neurons of the previous layer. And so the output of this neuron is it depends on the input wave coming to this and its transmission coefficient and also the wave propagation. So in this work, we model the wave propagation using like the Rayleigh-Sommerfeld diffraction theory. And using this, we can propagate the incoming field through this network. And after propagating through each layer, at the end, at the detector, we can get the intensity of this output field, so which is captured by the detector. So now, after modeling the D2NN, we can train the D2NN like for a given task, in like using a progression weights. And so for an example, if we consider an input field like this, so this is like an example task that I am like going to demonstrate. Like this one is like for face imaging. And so our input field here is like an amplitude with all ones, and like a phase. In the phase, we have like a miss digit. And so first of all, we have to do the forward propagation. So for that, we use the differentiable modeling that we did in the previously. And using that, we can model the entire propagate this incoming wave through the entire network. And we have like this output intensity as a function of each of these amplitude and phase coefficients of each of the layers. And after that, so we compute like an error considering the task that we are going to perform. So in this case, like we are going to do like a face imaging task. So what I'm going to do is like, we compute the loss with respect to the output, and this something like a proportional uh, something proportional to this input phase. So, and then during the optimization, we like try to find amplitude and phase coefficients that minimizes this error, and with these physical constraints. So these physical constraints are like these amplitude coefficients should be between 0 and 1 because our network is a passive one. And also the phase values are always like in between like 0 and 2 pi. And so after training this model, so this is like an example. So this is like this is like with the D2NN with like 5 layers, and we consider only like training we train only the phase coefficients. We keep the amplitude coefficients as 1, and for this network, like, so this is like the output we get for like phase as for the MNIST digit data set. And so with an SSIM of like around 0.77. And so these are the trained layers and their weight distribution. And now when we go to quantization aware training, so as I explained earlier, like in this fabrication techniques, we have the issue of this lack of precision. And to account for this, we have to do and therefore like we have to have like quantized weights in the network. And so one of the straightforward methods like to do this quantization is to do post quantization. That is that like, so we now have the full precision model. So we are like directly quantizing those full precision weights using a transfer function like a function like this. So this is like a hard quantization function, like a step function. And so in this, we assign each weight to a certain quantized level. And so when we do this to our trained network, the weight distribution becomes like this, but it heavily affects our result. So now the output intensity is like, so output is not as good as the previous one. And the SSIM and SSIM has dropped like significantly from 0.78 to 0.32. So therefore, like we can see, like we have to use like a quantization aware training process, like to maintain the performance as well as like quantizing the weights of the network. And so if we consider the previous function that I showed you, like, so we are like using gradient based optimization methods. And when using gradient based optimization with this function, there are like there are two issues we face. So one of them is like this function has these like sharp transitions, and the gradient in these transitions are undefined. So this function is not differentiable, and also at each level the gradient is zero. So it's not this using this function like to do gradient based optimization is not uh, not going to work well. So it's better that we like try to optimize the continuous weights, like instead of this discrete quantized weights. So to do that, we need to map the quantized weights to map the full map the continuous weights to quantized levels, but with a function which is differentiable and also which can approximate the hard quantization function. And for this, we propose a function like this, a soft quantization function, which is a summation of a series of sigmoids. And hence we call it like progressive soft sigmoid quantization. And so this is like the equation of this function. And it's, you can say like it's a summation of a series of shifted sigmoid functions. And in this function, if I just define like the terminally, like, so this L is like the lower bound of the quantized range, and delta is the step size between two quantization levels. N is the number of quantization levels, and this tau is one of the most important parameters in this. It's the temperature of the quantization, and this temperature actually plays like a major role in the training process. So if we have like a smaller temperature, as you can see in this red line here, so we have like a really soft function, and it doesn't even like show like quantized levels. This red curve, if you can see that. So it has like so if the temperature is low, like the weights have like more flexibility to like move around. And but when we increase the temperature gradually, like this function gets closer, like gets closer and closer to that hard quantization function. So using this function, yes, Dushan. Yeah, for the Zoom, because I think the question was like, we can like, whether we can like tweak this function like for non-uniform quantization, and the answer is yes, we can do that. So we can like superimpose like couple of these like things, and then we can like have non-uniform quantization. Yeah, and so using this temperature factor, like we uh, use like a progressive training approach for this quantization of our training. So the idea is like, so we start from like a smaller temperature, so where the rates have like more flexibility to move around, and then as the training progresses, we try to increase the temperature to make them like closer and closer to a fully quantized weight distribution. So for this, like we use like two approaches. So first one is like the linearly increasing temperature. So in this case, we start the temperature at a smaller value, and we are linearly increasing the temperature as the training progresses. And the second approach is the learnable temperature. And in this case, we make the temperature a learnable parameter so that the optimizer can optimize it as the training progresses. So if I go into a little bit more detail, so in the linearly increasing temperature case, for epoch, for the teeth epoch, like we can compute the error as this. Now you can see like in contrast to like the full precision model training, now our parameters. So here only I am only considering like the base parameters. So these parameters go through this soft quantization function to produce like during the forward propagation to get the output intensity. And this function like changes as with the epoch, and so that is because like this temperature is now like a linear function of the epoch. And during the optimization, as is like we try to like minimize this error, find phi that minimizes this error. And in the learnable temperature case, like it's a little different. Like, so now we compute our error like this. So in this, we have like two terms. This first term is like the loss uh, considering our task. So here you can see like we have this vector k. So this vector has like uh, a set of a set of parameters that are like, so we have like this a k parameter for each layer of the D2NN, and so this vector contains all these parameters, and these k values are directly like related to the temperature. I'll explain it. So then so now our function like, so this loss term like corresponds to the task, and also we have like a regularization term for the values of this k vector. Like we are trying to like reduce k as the training progresses, like we try to constrain. And so if we go into the our function, now the temperature for each layer is given by this like defined by k, and this gamma is a constant which prevents like this temperature from going into infinity. But and so now like if we take a look like, so when we what this regularization term do is like it tries to like constrain k. So and so during that process, like this k gets smaller, and when the k gets smaller, this temperature goes like tries to increase. So in the end, like this, what this regularization term does is like it tries to force the temperature to increase as the training progresses. So like So this regularization term like try to like keep the progressive training uh, approach while making this temperature like learnable. Yeah, this one is like a vector. So what? So this vector is like so. Yeah, it's a little bit confusing. This vector has like temperature values for each layer. So and in this function, I just consider like a one. If we consider one layer, like this is just a one temperature parameter. Index, yeah, yeah, that's right. Uh, yeah, and during the optimization, we try to find phi and this k vector, which minimizes the loss. So this is like an example of just a linearly increasing training approach. So you can see like we start like we start the temperature from a smaller value and we try to increase it as the training progresses. And when it increases, you can see these weights like get assigned like into quantized levels gradually. And also you can see the SSIM increases as the training progresses and the output intensity is much better than the post quantization case. And so for the evaluation of our method, so we consider an all optical quantitative estimation task. And for this, we consider like 3 data sets, MS digits, tiny ImageNet, and also an experimentally collected red blood cell data set. So in these data sets, like in all these data sets, we consider like the amplitude to be like all ones, and uh, the interested information is in the phase. And we compare the results of the full precision model, post quantization model, quantized model, and also like 3 other quantization aware training methods called the straight to estimator, lumbar softmax based quantization, and differentiable soft quantization. And also we can compare the results of 3 of our methods. So these 2 are like the methods that I explained previously, and this fixed temperature case is like in this we like fix the temperature and for in a certain value and like try to train the model. And so we use this like to demonstrate like the importance of like progressive training approach. With, yeah, yeah. Okay, sure. I'll check whether it's so published. So these are like this is like the comparison of the quantitative results and for each data set. So this green dashed line show like the full precision model performance in terms of SSIM. And for each data set, we consider 4 quantization levels, 8 levels, and 16 levels. And so we consider like the overall results. So this in each case, like these last 3 columns represents the results of our method, and the gray one is for the post quantization, and these 3 bars show the results of that other 3 quantization aware training methods. So if we consider like the overall results, like our methods like outperform these other methods like in almost all the cases, like except for like uh, just a couple of cases. But uh, so this differentiable of quantization is the one that performs much closer to our method. And yeah, and also like if we consider like for quantization levels, like the smallest number of quantization levels, like our method is like especially in this red blood cell data set, like you can see like it significantly outperforms DSQ. But also like we can see like the Gumbels of Max has like a higher SSIM in this case. But so if we go into the qualitative results, like I'll show you like uh, it's because of this data set. So this red blood the shape of the red blood cells, I think so we can see it in the qualitative results. And also like if we consider the progressive training approach in all the cases, like we can see like so this fixed temperature case is like so we the at least one of the progressive training methods like outperform like this fixed temperature case. Yeah, and also another thing to note is like in all these data sets, like this our methods like can like give like performance like really close to the full precision method, like with like 16 levels or 16 quantization levels. And so these are like the qualitative results for this is like one example of the from the red blood cell data set. And so this is like the input phase, and this is the full precision model results, and these are like results of different methods for different like 4, 8, and 16 quantization levels. And like if you consider this 4-level case, like so this is what I was talking about. Like so even though like Gumbels of Max had like higher SSIM values, like it is I think it's mainly due to this the shape of these red blood cells. Like so most of the red blood cells are like this annular kind of shape. So this network actually like trained with Gumbels of Max like predicts like most of the red blood cells has like this annular ring type of shape in the middle. So that actually has like increased the SSIM. Like you can see like in this dark region in the middle is like not actually circular. It's kind of like an oval shape, but here it's like a circular shape one. But in our method, like it kind of has that uh oval kind of shape. But yeah, so even though like this SSIM is higher, I think like our methods like have captured like the actual features of this like much better than this Gumbels of Max based one. Yes, Darshan. Uh, I use like the reverse Huber loss. It's a combination of L1 and L2 losses. Yeah, yeah. So that's one thing. So and the thing is like so I also like recorded L1 loss as well. But the thing was like the L1 loss also has like the same trend. So I was wondering like I'm not sure. So because like so L1 loss could be like a good measure, like because we are doing QPI, right? So yeah, so that's why like so even in the paper I thought of like a bit more analysis of like the qualitative results is like better. Yeah. Oh, so this one, you mean? Yeah. So it's like it's like so if we consider like the error, yeah, like so in certain parts like Gumbels of Max like has like a higher error, but also at the same time like some so it performs like marginal with like all the other cases as well. But in terms of the shape, I think like it so most cases it predicts like this annular kind of shape in the middle. Yeah, so I think like I like have like so I'm thinking of like putting like couple of examples in the paper, like one in the main text and also supplementary figures like with other examples as well. Yeah, but yeah. Yeah, classify. Yeah, most cases. Yeah. I'll classify between the. Mhm. Yeah. Mm-hmm. Okay. Please. Yeah. For the two classes. Yeah. So considering like the other two like quantization levels, like the output is like really good. Like it's like really like similar to the full precision output. And even like with the DSQ as well. Like so it performs like so our method like performs as well as DSQ. And so if we consider like the error plot, like you can see like when we go to like higher phase values in the red blood cell case, like in this particular example actually. So this our method has like a small error compared to DSQ. Yeah. And yeah. And these are like the results for the tiny MeshNet dataset. So in the tiny mesh dataset, like so with poor quantization levels, like or all the methods doesn't perform really well. I think like because of like the complexity. But so in these these last three in our methods, like there are like some small features, some features are visible, but the output is not that good. And but with like 8 quantization levels, like our methods like perform very well, and also like similar to DSQ as well. But so if we consider like the error for this 8 quantization level case, like uh, mostly like it's like the performance of DSQ and our methods are similar, but in certain areas like the error is like slightly less in our methods than the DSQ. Yeah. And finally for MNIST, yeah, and still like the core contestation levels like doesn't give that much of good results. But here, like in terms of like the shape of the digit, like I think our methods have captured it better than the other cases. And yeah, and also like so I forgot to mention like so for the network for the MNIST it has like less parameters because like here I think the layer is like 64 by 64 that 4096 neurons per layer, and in tiny meshnet and RPC we use like I think 200 by 200 size layers for each layer. Yeah, and this is like this report is like for 16 quantization levels, and this case like in this actually I think like all our three methods DSQ as like performing like similarly like it, and it's also like these results are really closer to like the full precision results. Yeah. So in conclusion, like considering like the fabrication and noise limitations in the training process of a D2N is important, and we can like handle the lack of precision by doing like a quantization aware training with a soft quantization function. And our proposed method uh, performs the quantization aware training methods, other quantization aware training methods like in most cases, and also it's able to like give like a similar performance compared to the full precision model with like a smaller bit at like 4 bits. Yeah, uh, that's all I have. Yeah, if you have any questions. Yeah, so so hyperparameters like we use in this case, like specific to this case, are is like the so one is like this mu, and also like this gamma also like plays a role, but because like it put like a cap on like where the temperature can go, and also like this the way that we increase this lambda. So we use like several different methods like to increase this. Like one is like it would be we did like the linear increasing of this, and also so I think the best work one is like so we increase the lambda in like up as like a power of 2, like so we like at like so at like each 5 epochs we increase it slightly, like as a power of 2 epoch, as a function of the epoch now. Yeah. Yeah. Yeah, it has. Yeah, but there are some hyperparameters we have to tune for that as well. Yeah. Because like if we don't add this regularizer, what happens is like it doesn't like learn where like it like the temperature doesn't, so this progressive nature of the training doesn't hold to that, because like it can easily like increase the training set performance by like reducing the temperature